This one's really getting quite technical, a little bit in your wheelhouse to some extent, although I love it because we're talking about pronouns and labels and things today. I want to confess to you my worst mistake at ThoughtWorks, which was the day I called a data engineer a data scientist. And I'm still applying the burn cream from the result of what I got back, saying they're not the same thing, Nigel. Now, this is a great opportunity to learn what one of those roles does. What have we got coming up?
Sure. We're happy to welcome Gargi Ahluwalia. She goes with the pronoun she, her. So Gargi is a data engineer and a lot of experience in that space. And she started with ThoughtWorks at the start of this year. And she got to work on an exciting problem where they are working to bring together the traditional SQL and the NoSQL world. So Gargi, tell us all about how we can actually still have that horizontal scaling, but with maintaining all the relational,
As a data engineering consultant at ThoughtWorks, I have recently come across distributed SQL databases. And when I first heard the term NewSQL, it was quite new to me. But over the course of 6 months, I learned a lot about these databases, and I thought it would be nice to share it with the wider community. And so today, I'm going to share my experience evaluating the capabilities of distributed SQL, which is a subset of NewSQL databases, and talk about the areas where they shine. But first, let's look into the history of databases. Computerized databases were introduced in the 1960s, but their popularity only started to grow after Edgar Codd released a paper in the early 1970s, which formed the basis for relational databases. In the late 1970s, Oracle released the first commercial relational database, followed by IBM and others. The term Relational Database Management System was also introduced in the 1970s. During this time, storage was extremely expensive, and these systems were designed to make the best possible use of the available storage. In the 1980s, SQL became the language for querying data, and many important features such as table joins and indices were added. The mid-90s saw the release of 2 major open-source household relational database management systems we know today, PostgreSQL and MySQL. These databases were very popular among the businesses even today for reasons well known. However, towards the late 90s and early 2000s, with the growth in popularity of Internet, many large companies were beginning to hit limits in their ability to scale these traditional databases, and so these companies went on to search for alternatives. In 2007, Google released its white paper describing a non-relational key-value database called Bigtable, and hence a new class of databases called NoSQL arrived. Since Google's Bigtable, we have seen the emergence of many other NoSQL databases such as DynamoDB, MongoDB, Cassandra, Redis, etc. Now, these NoSQL databases focused on speed, scalability, and availability and sacrificed consistency in the process. While they were a great fit for many of the use cases, their lack of traditional features such as table joins and transactional consistency and ACID compliance were some of the reasons that they didn't see much wider adoption. Also, huge amount of investment was required for companies to move applications running on a relational data store to a non-relational key-value data store. This was the reason that these NoSQL companies were trying to become more SQL-like by adding features such as table joins, ACID compliance, SQL query language. And also during this time, storage was becoming cheaper and the SSDs were on the rise. While all this was happening, there was another group of people thinking, Why can't we just design a better relational database? The key idea was to design a system that would provide the scalability and flexibility of a NoSQL database while still retaining the support for SQL query and ACID compliance. And hence, a new class of databases called NewSQL arrived. The first in the class was Google Spanner, followed by companies such as VoltDB, NeoDB. While these NewSQL companies didn't see much success in the early years, towards the end of 2010, there was another bunch of companies that took the same concept as NewSQL and added enterprise-like features to it and cloud support and named it as Distributed SQL. Distributed SQL companies such as CockroachDB, YugabyteDB have seen much wider success in the last 5 to 7 years. Now, when I was preparing this talk, my mentor and I, we realized that talking about databases can be a bit dry. So in order to motivate you for this talk, I have created a hypothetical company called Walkmate, and also since I love walking outdoors. And with the example of Walkmate today, I will walk you through what challenges they are facing as a young and growing company and how Distributed SQL can help solve those challenges. So a bit of background about Walkmate. It's a unique social platform that gets people out walking together. Think of it as an Uber of walking. You can also earn rewards by walking in teams. The company started in Australia, but owing to a recent success, they want to expand overseas. And the architecture of Walkmate is a simple Ruby on Rails application running on PostgreSQL RDS database. Recently, Walkmate organized an annual walking event called Walkathon. And in this walkathon, thousands of you subscribers were expected to join. The Walkmates team were working really hard for this event. They migrated to a larger database instance, they added failover instances, and load tested up to 1 million users, which was 5 times the numbers they were expecting. Everything looked great until the night before the event. The following tweet got sent by a well-known Australian celebrity. And the next day, more than 1 million subscribers logged in. While Walkmate services scaled to meet the demand, their database was under high constraint due to large number of concurrent connections. While the team succeeded through the day, there were a lot of complaints from users about slowness in the app. Now let's see how Walkmate can mitigate this in future. The first obvious option would be to migrate the existing relational database to a larger instance, that is, scale vertically. However, and assuming they have not already done so. However, this can have a blast radius problem where an outage can affect the users. The other option would be to manually shard the relational database by adding a routing layer which would take all the queries and route them to the nodes where the data is located. However, this would mean that Walkmate's engineers would now have to spend all their time and energy in designing this complex routing logic. While there are a lot of libraries available, manual sharding is still quite complex. There would be other challenges too, such as elastic and dynamic scaling would be difficult, and there may or may not be a natural sharding key or primary key present in the Walkmate schema design, which means that they might have to change their schema design. The second option would be to adopt a NoSQL database, such as DynamoDB. Now, this would provide horizontal scalability, but would also mean that Walkmate has to move from a relational data design to a non-relational key-value data model. Also, their developers might have to learn a different query language, and there may or may not be support for table joins and transactional consistency, which is important for Walkmate. The third option would be to adopt a distributed SQL database such as CockroachDB. Now, this would scale horizontally, be SQL native with support for table joins. It will also provide support for ACID compliance and transactional consistency. And also, sharding and replication of data would be automatic. Now, out of these three options, distributed SQL seems pretty compelling. So let's see how it achieves some of these capabilities and what are the things that needs to be traded off to achieve these capabilities. Let's start by understanding the architecture of a distributed SQL database. The architecture looks like a single logical SQL database. However, it's actually a cluster or group of nodes. Each node has two layers. The top layer is a SQL API which converts the SQL statements, the high-level SQL statements, into low-level read and write requests to the underlying data storage layer. The data is stored in the data storage layer in the form of a monolithic sorted map of key value pairs. Now, this key space is further divided into ranges or contiguous chunks of data based on a primary or composite key. These ranges are not stored on just one node, but are split evenly across the nodes in the cluster. And each range has a limit to its size. So if the data in one of the ranges increases, the range splits within the node. Now, storing data in the form of ranges is all well and good. But what about fault tolerance? So in order to ensure fault tolerance, each range is copied or replicated to other nodes in the cluster. By default, each range has 3 copies or replicas, which means a replication factor of 3. Now let's look at the read and write scenario in a distributed SQL database. In a traditional relational database, the read scenario is simple. The application sends the read query to the database, and database responds with the data back to the application. However, in a distributed SQL database, the read scenario looks slightly different. Let's consider this example of a 3-node cluster which has 3 ranges, and each range has 3 replicas or copies. Here, the node 2 is the gateway node, which receives a request from the application to read from range 3. Now, since the leader or the primary point of contact for range 3 is on node 3, node 2 sends the request to node 3, node 3 responds with the data to node 2, and node 2 responds to the application. The important point to note here is that if node 3 was the gateway node, the number of hops in the process would reduce. Now let's look at a read-write scenario. Again, in a traditional relational database, the application sends the write request or query to the database, and database acknowledges the write. However, in a distributed SQL cluster, the write scenario is slightly more complex. This is because the data needs to be synced across all the 3 replicas using a distributed consensus algorithm, such as Paxos or Raft. Now let's consider this example again. Here, node 1 is the gateway node, which receives the request from the application to read from range 1. Now, since the leader for range 1 is on node 1, it appends the writes to its own log and notifies the follower replicas on node 2 and node 3. Node 2 acknowledges the write, and hence we have achieved a write consensus. Node 1 then responds to the application. The follower replica on node 3, which was not involved in this consensus, appends the write to its log as soon as the others have done so. The important point to note here is that not all replicas are involved in achieving the write consensus. Only a majority is required. So if you have a replication factor of 3, only 2 replicas are required to reach a write consensus. And if you have a replication factor of 5, 3 replicas would be required, and so on. Now, having looked at the read and write scenario, let's understand how these databases scale. Scaling is pretty simple. It's as simple as adding new machines, and rebalancing and replication of data is done transparently by the system. There is no need to do manual sharding or add complex routing logic, which is required to scale a traditional relational database. And also, since any node can support read and write requests, a higher number of concurrent connections can be supported. However, there are a couple of considerations and trade-offs in terms of performance of these databases. Firstly, the schema design is very crucial, and how you partition the data across the clusters, across the nodes in the cluster is very important to achieving benefits of distributed SQL. It is a bit of an art. The general guidance is to partition your data in such a way that it is distributed evenly across the nodes in the cluster. Try and avoid simple incrementing and time-based primary keys, which would mean that all your recent data is stored in just one node, leaving that node to handle all the traffic. Techniques such as hash-based partitioning, which means random distribution of data across the nodes, is one way to solve this. The other consideration is that scaling up and down have different considerations. Scaling up is easy, just add new nodes and the database replicates and rebalances the data itself. However, when scaling down, one needs to be quite careful. If you remove too many nodes at the same time, you are at risk of losing the write consensus required to achieve the writes. And if you remove the nodes too fast, you can end up having a replication storm, which means that your cluster is so busy replicating data across the nodes that it will not be able to serve the read and write request, leading to downtime. So scaling down needs to be done carefully. Also, in terms of performance, it's not all roses. These databases need more hardware to achieve similar raw throughput compared to a traditional relational database. Now, this is somewhat intuitive, given that they have to do a bit more work in terms of read and especially for writes, as we have seen before. Also, one needs to be very careful when designing schemas and workloads that involve range queries, which require joining and scanning over large ranges of data. If data is not partitioned carefully, such queries can be very expensive and lead to poor performance. So these are a few considerations and performance trade-offs that you need to keep in mind. Now let's return to our hypothetical app Walkmate for a bit, as there is a new requirement that has surfaced. Walkmate has seen huge success in Australia, and now they have users in New Zealand downloading the app. However, they are having some reports that the users in New Zealand aren't happy. Apparently, there are some lags in their updates for their walking teams, and just to complicate things further, the New Zealand government has introduced some new data privacy laws, which state that all personal user data must reside within the New Zealand borders. So let's see how Walkmate can resolve these with the existing traditional relational database. Now, this would involve all the problems of manual sharding as we have discussed before, but just even more complex. The complexity of routing would be massive. Scaling and resharding per region would be quite difficult. Partitioning of data into global and regional tables and then replication of data across the regions would be a challenge. Not to mention the complexities involved in deployment and operation of a distributed SQL cluster in a multi-region setting. However, on the other hand, in the distributed SQL world, one of the major features on offer is the support for multi-region clusters. Most distributed SQL vendors provide fine-grained control of data locality, which allows you to optimize performance across geographical regions. To understand this, let's consider this example of a cluster which is spread across 3 regions. Imagine that this table has 10 rows, 5 of which are set to locality AU and 5 are set to locality NZ. To ensure fast reads and writes for the NZ users, the 5 rows are optimized by placing the leader and the voting replicas within the NZ region. Now, this means that a write would not have to cross another region because, remember, for a replication factor of 3, you only need 2 replicas to reach a write consensus. And similarly, to optimize performance for the AU data, the leader and the voting replicas would be placed in the AU region. Now, placing data in this manner ensures that it is present closest to where it is accessed from. This reduces latency and improves application performance. Data can also be partitioned into global and regional tables. Global tables are optimized for fast reads by placing 1 replica in each region. So it is useful if you have a table which has high number of reads but low number of writes, as the writes would be slower for a global table. Similarly, in a regional table, the data in a given table is optimized for fast reads and writes within the same region. So imagine instead of rows, this is an entire table. And this is done by placing the leader and the voting replica in the same region, which means that the reads and writes would be quite fast in the AU region, whereas writes from other regions would have to consult AU region. Now, distributed SQL can also help Walkmate solve the data residency requirements. The new laws state that all personal data must reside within the NZ borders. Distributed SQL can do this by pinning specific tables or even rows to locality NZ. Now consider this example from the previous diagram where the user data for NZ was optimized for fast reads and writes by placing the leader and the voting replicas in the NZ region. But in order to follow the data residency guidelines, the rows or tables containing the personal user data would be present only in the NZ region, including all of its replicas. Now, this has a bit of trade-off because in case there is a natural disaster and the entire NZ region goes down, the personal user data would be lost as there is no other replica present in any other region. So this brings us to talk about high availability and fault tolerance. Distributed SQL databases provide high availability and fault tolerance capabilities. You can tune your cluster to support a zone outage or a region outage. Now, in case you want to survive a zone outage, the database will place the leader and all of the replicas in the same region. And this means that the reads and writes would be quite fast in the AU region. And in case one of the zone goes down, as shown in this diagram, you still have 2 replicas available in the zone to support the read and write request, which means 0 downtime. And in case you want to survive a region outage, the database will place 5 replicas as shown in this diagram, which means that a write would only have to consult one other region to reach a write consensus, because for a replication factor of 5, you need 3 replicas. And in case the entire region goes down, you still have 3 replicas present in the cluster to support the read and write request, which means 0 downtime again. So whichever option you choose, you need to keep in mind that there would be some trade-off between high availability and latency. Now, having looked at some of the features of distributed SQL, here is the question to you. Should you embrace distributed SQL? Now, if you are happy with your relational database, you don't need to scale, you don't need multi-region support, you don't need to follow data residency guidelines, then you can stay with your database. However, if you do need your relational database to scale horizontally, not just for reads, but also for writes, if you also want your data model to be strongly consistent, provide transaction support, ACID compliance, SQL query language, or you need your cluster to be highly available and fault tolerant, or you need to spread your data across multiple regions and follow the data residency guidelines, then you should evaluate distributed SQL as per your use case and see if it could benefit you. As far as the WalkMe team is concerned, they are quite happy to have a new tool in their toolkit, and stay tuned for the upcoming features in the WalkMe app, and see you at the next walkathon. But before we move on to questions, a big thank you to my mentors, Keith and Simon, who have helped me throughout my journey to prepare this talk and provided their valuable feedback.